Yes, yes, yes. Welcome to another Alt Dev Log a Day video. Another hastily thrown together, not very well researched, probably doesn't even work, and may not even be that interesting extravaganza. All right, so this time I would like to talk about an interesting problem that was given to me by my good friend, genius and a half, pride of Naughty Dog Ice Team, Cort Danger Stratton. Now, I didn't actually get Cort's permission to use his picture in this video, so I have to approximate him, and I'm going to do that using a technique I like to call strategetical Cortmonics. It's very similar to spherical harmonics, except instead of orthonormal basis functions defined on the surface of a sphere, you're using orthonormal faces functions defined in Google image search. And you want to go ahead and recreate the original signal, which is Cort's head, by weighting these things and then summing them up to reconstruct. So I'm going to go ahead and give Carrot Top 0.8, Indiana Jones 1.5, and Neo 0.06. That's Cort. And the result is 101% dangerous. All right, cool. So here's the actual challenge. He wanted me to implement what I assume is floating point absolute value using only SPU odd instructions. I can't touch any even ones. You're allowed to load any data you want, but you're not allowed to use any lookup tables. Okay, so what do I mean by odd instructions? I will cover that in a few minutes. However, I would like to point out that these instructions look pretty odd. Turns out that one of them is not, and another one is not actually a real instruction. Okay, cool. So let's just jump right in and look at what a floating point absolute value would look like using even instructions. Okay, cool. So I'm going to go ahead and take the floating point and represent it in IEEE, as hex. Now, for those of you who are not familiar with floating point format, it breaks down like this. You have the bottom 23 bits, least significant, is the mantissa. Now, I'm not going to go into the details because mantissa explains it all. Next, you have the exponent, bits 23 through 30, and the thing we actually care about is the sign bit, which is bit 31, most significant bit. If we could take that one, that most significant one, and make it a 0, then we have a positive number. Okay, so if you look at the original number, I'm going to go ahead and use -1 as an example, and look at it in binary. That thing I just circled is the sign bit. We want to find a way to 0 it out. So if you take it and mask it and AND it with 0x7FFFFFFF, which for those of you who don't know hex, that's just a 0 for the most significant bit and then 1 for everything else, it has the effect of copying the original value but zeroing out the top, which in this case turns negative to positive. So we're done, right? Oh, sorry, there's the sign bit. And now we're done. However, like I said before, AND on the SPUs is actually an even instruction. And I don't expect you to know what that means, but just remember the rules say we can only use odd instructions. So we can't do it the traditional way. So let's go ahead and talk about what even and odd means a little bit, just to give you an idea. All right, so here is a picture that I took off Google Images from IBM. The SPU actually has two pipelines. There's an even and an odd pipeline. Even is things like your floating point unit, fixed point unit, integer instructions, stuff like that. Odd tends to be, we have permute, loads and stores, some DMA stuff, branch unit, things like that. Now the cool thing is that if you have an even and an odd instruction, and they fall on a particular alignment, and one doesn't depend on the result of the other, you can actually issue them at the exact same time. You can dual issue. And one of the main goals in SPU optimization is you really want to get as much dual issuing as you can. You want to use the hardware to its full potential, not only half use it by only using one pipeline. So to give you a more clear idea of what's going on, I will show you some actual code from a static analyzer. Or I can suggest that you go ahead and look at Insomniac's excellent SPU cheat sheet, but be careful what version you get. I believe, if I remember correctly, in an older version, the even and the odds were swapped, but that was fixed later on, so definitely check it out. It's probably the best reference out there for this kind of stuff. It's a PDF. Okay, here we go. Here's the example. So even pipe is on the left, odd pipe is on the right. Each individual row represents one cycle. If there's a red instruction and a blue instruction, that means you can issue two instructions at the same time. If you only see blue, it means you can do an odd but no even, and then vice versa. So if you notice, the odd pipe has really, really good utilization. I mean, it's basically 100% busy except for 2 cycles at the end. So that's the blue instructions. Not the case with red. With the red, there seems to be a huge gap, which I've circled. Oh my god, what the fuck? Oh god. Oh, I did not mean to say that. Trying to keep it family friendly. Sorry. What the... Huh? Yeah, so if we could take something that used to be done in odd instructions, even if we convert, when we do it in even instructions, even if it takes 4 instructions instead of 1, it may still turn out to be a win because we're using this spare unused time on the even, and then it frees up space on the odd that we can do more odd stuff. Now, what we have is the opposite problem. In Cort's problem that he gave to me, we basically are assuming that we can't use even instructions because the even pipe is full, but we want to use odd. So we're trying to take something that used to be even, like an absolute value, and do it using odd. All right, so here's the general gist. I have a vector of 2 elements. Pretend that each element is 32 bits. I drew it as 16 bits to make it fit on the screen. So essentially what we want to do is this. We want to do a whole vector rotate. So if you notice, in a whole vector rotate, elements can actually swap places. So if you look at the sign bit of the vector element on the right, it used to be in that most significant bit place, and we shifted it. Now it's the least significant bit of the element on the left. So it basically just takes the whole vector like it was some monolithic 128-bit thing and just rotates it, takes stuff out the end, attaches it to the start again. So the important thing to notice is what used to be the sign bit has now been shifted over into the next element. And we do this using ROTQBII, rotate quad word by bits immediate, which luckily happens to be odd. Now, here's the trick. Here's how we're going to do this. If there was some magical way to zero out that vector element on the left, like that, and then rotate it back to the right, essentially we have in that rightmost element the original value except a 0 where there used to be a 1 for the sign bit. We have officially made it positive, or definitely kept it from being negative. Okay, one more thing you have to know before we get into the actual solution is just that the SPU register set is unified. So what does that mean? Normally on CPUs you might be used to, you have a separate set of registers for floats, and a separate set of registers for int, and a separate set of registers for vector. On the SPUs, there's just one set, everything is vector, and how the bits in it are treated depends on the instruction you call. So if you call an instruction that operates on words, it's going to treat it like a vector of 4 words. If you call an instruction that operates on bytes, it's going to treat it like it's a vector of 16 bytes. Now, just be careful, because if I start with a float in the register and then I call an integer instruction on it, there's no conversion, there's no truncation, there's nothing. It just takes the bits that were in there from the result and just pretends that, just interprets them like they were an integer. So that becomes super useful right about now. Okay, good. Here's the actual solution. So we want to go ahead and crank up the resolution to 1080p because I actually do have 128 bits going across the screen right now. It'd be a good idea if you want to see what's going on. The sign bit of each float is in green. I kind of got lazy halfway through the video and just made them all -1, but it works. So step 1, like I said before, is you want to rotate the entire vector 1 bit to the left. So taking those green sign bits and moving them to the vector element to the left. Like that. Okay, now I'm going to circle some stuff that I want to bring your attention to. Now these areas contain the bytes. They're 8 bits. They contain the byte where the sign bit would have been if it was in there. Like the sign bit would have been within this red circle if we hadn't just rotated it. So there's still some useful information in there, but not the sign bit anymore. Okay, now I'm going to take a bit of a leap. I'm going to have you believe that there's a magical instruction that does what I'm about to explain. Okay, so what we want to do is we want to take that rotated vector, the red circles, and we want to insert those bytes into a destination vector. And then we want to insert zeros in between them so that we have 0 first red circle, 0, second red circle, 0, third red circle, and so on. And the reason we're doing this is what I said before. We want to zero it out so that if we shift it back again to the right, we take that 0 and we make it the sign bit. So I'm going to go ahead and rotate to the right. Now, here's our result. And we're going to take those non-zero bytes and we're going to insert them back in. Now, if you look at the source, the vector we started with, and then this one, they are exactly the same, except we have cleared the sign bit, making the negatives positive. Now, I explained to you the magic instruction behind it all. Okay, cool. So SHUFB takes 3 vectors as an input. Input number 1 is just a bunch of bytes. The things in blue, by the way, I'm just indexing the elements so you know that that first thing is 0, the second thing is 1, the third thing is 2. The data the vector contains is the thing on the bottom. Another input full of some random values, a mask, which I have not explained, and the output. So essentially what we're going to do is I'm gonna make up some values for the select mask, and then hopefully from that you'll understand what it's doing. Okay, so 2, right? It's a good number. Why not? So what we're going to do is we're going to look in input 1 and 2 for something with an index of 2, that thing in the blue, and it is right up there, red circle. Then we're going to copy the data, which is 0.77, to the output vector. I mean, it's pretty obvious what it's doing, but I'll do it this 4 more times just for fun. Next, hex 14. All right, so go ahead and look at input 1 and 2, the blue areas, and try to find 14. There you go. And its value is DE. Data is DE. We copy it. Same thing with 1D. 1D is going to be input 2 towards the end. Yep. And its value looks like it's DC. Data is DC, so we copy that in. And finally, one more example, 0D. 0D is first vector towards the end also, D4. All right, so its data is D4, copy that in. Now, I said not only do we want to grab bytes from the source vector, if you think about the previous the previous algorithm I explained, but we also want to insert zeros. So would that be a whole nother instruction? Do we have to do something to zero it out? Luckily with SHUFB, there are magical values that allow you to insert useful constants. So for example, here I have hex 80. Now, if you look at input 1 and 2, the indexes, obviously there's nothing there even close to hex 80. So what this means is this is a special signal to SHUFB to say, go ahead and in this slot, insert a 0. Another one is C0. C0 should give you all Fs. So not only can you select from 2 input vectors and make a new vector, but you can also insert, you know, some useful constants. Okay, and here are all the constants you can do. The thing where you're selecting from the input vector, that's the otherwise case at the bottom. You probably have that totally down. Because each selection element in your mask is a byte, if the pattern starts with 1, 0, it outputs a constant 0. If it starts with 1, 1, 0, it's FF. If it starts with 1, 1, 1, it's 80. So you can actually build a fairly large number of really, really useful, commonly used constants out of this. And that's about it. So I like to end with a joke. The ball is in your court. It's fairly, if you've done some SPU programming, it's fairly obvious what to do at this point, but I didn't actually specify what the selection mask should be to accomplish the steps that I told you in the actual algorithm for doing it. That is left up to the reader as an exercise. There's a more efficient way to do this than I had posted in this video, so I challenge you guys to come up with it, figure out what it is, and then maybe I will answer again, see if I can do a couple cycles better than you, and we'll leave it in the comments, and we'll see if we can get a little back and forth going. It'll be fun. Also, I basically did this in my head. I never tested it. I never ran the code. I could have missed something. Like I eyeballed and it looked right, but what do I know? So if you see a mistake in it, definitely let me know, and I will try and correct it. Cool. Hope you enjoyed it. Got some free time coming up, so if you want me to make another video and you have a request, feel free to go ahead and leave that. And if you like the video, just let me know. Cool, because I appreciate it. Thank you.